RSC from scratch, part 1, server components. So recently, Dan Abramov had this really incredible article where he did a technical deep dive with a simplified version of React server components from scratch. And he asked on Twitter if anybody wanted to try to turn it into a YouTube video because it's written literally like a script. So I'm going to try my best to do a bit of a dramatic reading here. I've got the first version of the app here, and we're going to update it as we go with each new version that he gives us. And I'm going to explain a little bit, but I'm going to try mostly to keep this in his words. So here we go. RSC from scratch, part 1, server components. Seriously, this is a deep dive. This deep dive doesn't explain the benefits of React server components, how to implement an app using RSC, or how to implement a framework using them. Instead, it walks you through the process of inventing them on your own from scratch. This is a deep dive for people who like to learn new technologies by implementing them from scratch. It assumes some background in web programming and some familiarity with React. This deep dive is not intended as an introduction on how to use server components. They're working to document server components on the React website. In the meantime, if your framework supports server components, please refer to its docs. For pedagogical reasons, our implementation will be significantly less efficient than the real one used by React. We will note future optimization opportunities in the text, but we will strongly prioritize conceptual clarity over efficiency. So, let's jump back in time. Suppose that you woke up one morning and found out it's 2003 again. Web development is still in its infancy. Let's say you want to create a personal blog website that shows content from text files on your server. In PHP, it could look like this, where you define your variables at the top, and you get the contents of a text file, and you echo it into the article tag, and then you put the author variable in the bottom, and you create a copyright with it. We're going to pretend that tags like nav, article, and footer existed back then to keep the HTML easy to read. When you open up localhost 3000/hello world in your browser, this PHP script returns an HTML page with the blog post from post hello-world.text. An equivalent Node.js script written using today's Node.js APIs might look like this, where we import the create server method from the HTTP library, we import the read file method from the FS promises library, and then we import escape HTML, the only outside library that we use other than NodeMon. And so we're going to create this server where we just define our variables at the top, and then we create a string template that we passed into this send HTML function, and then we can, at the bottom, just set the status code, set the header, and send that string of HTML. And then imagine that you could take a CD-ROM with a working Node.js engine back to 2003, and you could run this code on the server. If you wanted to bring a React-flavored paradigm to that world, what features would you add, and in what order? So really quickly, let's look at the code that we have here. And we have the function here. We have everything. It works perfectly. We can see over here we have the hello world.text. If we edit it and we save and we refresh, then we will see the new edit on the screen. Everything works great. Let's keep moving. Step 1. Let's invent JSX. The first thing that's not ideal about the code above is direct string manipulation. Notice that you've had to call escape HTML post content to ensure that you don't accidentally treat content from a text file as HTML. One way you could solve this is by splitting your logic from your template, and then introducing a separate templating language that provides a way to inject dynamic values for text and attributes, escapes text content safely, and provides a domain-specific syntax for conditions and loops. That's the approach taken by some of the most popular server-centric frameworks in the 2000s. However, your existing knowledge of React might inspire you to do this instead, where we take it out of a string and we don't use the escape HTML function, we just put the curly braces around our variables. This looks similar, but our template is not a string anymore. Instead of writing string interpolation code, we're putting a subset of XML into JavaScript. In other words, we've just invented JSX. JSX lets you keep markup close to the related rendering logic, but unlike string interpolation, it prevents mistakes like mismatching open-close HTML tags or forgetting to escape text content. Under the hood, JSX produces a tree of objects that look like this. The most important thing here is the double $ type of symbol for React.element. That's what tells React that it's a JSX element. Underneath we have the type. Right now that's just the HTML tag, HTML head, body, nav, and then we have the props. Right now the most important prop is children, which is just more of these objects nested within each other, although some of them we have like the href attribute right here. So, however, in the end, what you need to send to the browser is HTML, not a JSON tree, at least for now. Let's write a function that turns your JSX into an HTML string. To do this, we need to specify how different types of nodes, a string, a number, an array, or a JSX node with children, should turn into pieces of HTML. So we have this function, render JSX to HTML, which takes in some JSX, checks to see if it's a string or a number. If that's the case, then it's just going to escape the HTML and put it into the template. Next, we check to see if it's an empty node by looking to see if it's null or the type of Boolean, and then we just return nothing for that. It's an empty node. Next, we check to see if it's an array. And if it's an array, we're going to map through it and then run this function on each of its children and join them together with nothing in between. Lastly, we check to see if it's an object. If it's an object, we then check to see if it has that double $ type of symbol for React.element. And if that's the case, then we're going to turn it into an HTML tag. So we open up the HTML tag, place the JSX.type inside of it, which remember was just the HTML tag for now. And then inside of that, we loop through each of the props for that specific thing. And we check to see if it's supposed to be there and if it's not a children prop. If that's the case, then we're going to put it inside of the HTML tag. So we put a space in between each one, we put the key equals the value. And then we close that, close the opening tag, render the JSX to HTML for each of the children inside of it, and then we close the HTML tag and we return it. And then finally, we check to see if it's an object that does not have the double $ type of here. And if that's the case, then we know that it's a normal object that's not a React element. We can't render that. And then we then know that if it's anything else, like a functional component, for instance, that's not been implemented yet. So let's go check out the code for this and let's go change our code over. Okay, so we'll start off by copying and pasting this new create server function. And I'm actually going to change this port because Code Sandbox is struggling. And then down here, we're going to change the send to HTML function. And we're going to change this into JSX that it's taking in. And now we define the HTML by using this new render JSX to HTML function that he has given us down here. And we'll just copy and paste that guy over. Now, unfortunately, this still isn't gonna quite work. And we'll see here that if we restart the server, so we see this error here, and it's the unexpected token with the less than symbol. And that's because this is not valid JavaScript. This is valid HTML, but we need to use something to transform the valid HTML into this tree of objects that we saw. And so that's going to be Babel. And so we're going to use Babel and the special plugin transform React JSX. But the problem with this is we still actually do technically need React because it's getting the JSX runtime from inside of the React library. So we're not actually going to be using React to do any of our rendering. We're going to be using our special custom function that he gave us, but we do need React technically for the JSX runtime to work correctly. So we will just install all of this. So now we have Babel and React, and we are able to do the JSX transform, but we actually still need to help it understand what we're trying to do here. So we need to create this other file, node.jsxloader.js. And inside of here, I'm just going to copy and paste this code. This is not important to understand. It's just telling Babel how to do things. So we'll just copy and paste that, save that. And now we need to actually run this. And so instead of just running the server.js, we're actually going to run the experimental loader that we have given it here. So let's copy and paste that in. And now if we save this, go over to this, we should have a working version of the app. Let's restart the server just in case. Okay, I literally didn't change anything at all whatsoever. Code Sandbox is just having a really rough day. So whenever we save this and we refresh this, then we can see that it works perfectly. Step 2, let's invent components. After JSX, the next feature you'll probably want is components. Regardless of whether your code runs on the client or on the server, it makes sense to split the UI apart into different pieces, give them names, and pass information to them by props. Let's break the previous example apart into two components called blog post page and footer. And blog post page is most of the content, but it has the footer component inside of it, and it passes it the author prop, and inside of that we create the copyright. So then we can replace the inline JSX tree we had with that functional component. And so that really simplifies the send HTML code right here. So let's go ahead and copy and paste all of this over and see how this works. And let's go take a look over here and we'll refresh. And that's not right. Let's see what's going on here. If we open this in another window, and then we look inside of this, it's got the function definition. This is broken down into the JSX here. So let's go back and see what's going on. If you try to run this code without any changes to your render JSX to HTML implementation, the resulting HTML will look broken, as we saw. The problem is that our render JSX to HTML function assumes that JSX.type is always a string with the HTML tag name, such as HTML, footer, or P. But here, blog post page is a function, so doing less than plus JSX type plus greater than prints its source code. You don't want to send that function's code in an HTML tag name. Instead, let's call this function and serialize the JSX that it returns into HTML. So we need to add this else if into here. So we're going to copy that. And then we're going to go back over here into our server. Go into the render JSX here, and so we are going to put it right here. Boom, and then we save this, and we go over to our example, and we refresh, and it works again. Yay! So this just takes in the component, which is the JSX type, sees that it has the props, and it calls the function with those props, and then it returns this very same function recursively with that returned JSX. Now, if you encounter a JSX element like blog post page, author, JDo, while generating HTML, you will call blog post page as a function, passing the author to that function. That function will return some more JSX, and you already know how to deal with JSX. You pass it back to render JSX to HTML, which continues generating HTML from it. This change alone is enough to add support for components and passing props. Step 3. Let's add some routing. Now that we got basic support for components working, it would be nice to add a few more pages to the blog. Let's say a URL like /hello world needs to show an individual blog post page with the content from /post/hello world.txt, while requesting the root /URL needs to show a long index page with the content from every blog post. This means we'll want to add a new blog index page that shares a layout with blog post page, but has different content inside. Currently, the blog post page component represents the entire page from the very HTML root. Let's extract the shared UI parts between pages, the header and the footer, out of the blog post page into a reusable blog layout component, which just takes in some children, defines the author of JDo, and then puts the nav and the footer and the head all around the children in the main tag. It's using the author in the footer right here. We'll change the blog post page component to only include the content we want to slot inside of that layout. So blog post page takes in a post slug and post content, creates a header with a link to that post slug, and then the article underneath of it. Here is how a blog post page will look when nested inside of a blog layout. Let's also try to add a new blog index page component that shows every post in the post folder one after another. So it's a section with a big header, welcome to my blog, and inside of that is a div that takes in some post slugs and maps through them, and very similarly creates a header with the article inside of it. Then you can nest it inside a blog layout too, so it has the same header and footer. Finally, let's change the server handler to pick the page based on the URL, load the data for it, and render that page inside of a layout. So the create server function here, it just tries to make a URL based on the request URL and match the route with this function down here that we're about to go over. And then it sends the HTML if the page is not null with the blog layout surrounding the page. Otherwise, it sets the status code to 404 and sends a header not found. And if there's any error, it sets the status code at 500 and sends a server error. And then the match route function checks to see if we are on the root route, which in that is the case if it needs to read the entire post directory. And then it creates the slugs by mapping through each of those files it finds in the directory and slicing it before the period. And then with each of those, it maps through them and reads each file. And then it returns the blog index page with the post slugs and the post contents. Otherwise, we're showing an individual blog post. These are the only other pages that we have. We've sanitized the file name with this outside library that we're bringing in, and then we try to read the file and return the blog post page. Otherwise, we return null. Now you can navigate around the blog. However, the code's getting a bit verbose and clunky. We'll solve that next. So let's get all this code copied and pasted over here. First, we need the layout and the components. And we need to change over our create server function. And I brought in that match route function that he had there. I need to change this port again, annoyingly. And then lastly, we can't forget to bring in the sanitized file name library. And we can't forget to bring in the read dir. So we bring in the sanitized file name. We're going to change the port again because it will never let us close a process. And now when we save this, this should work over here. We click on it, we have this. And now whenever we bring in a new text file, which we can do like this, hi.text, and this is a different one. Now, when we go back over here, we go to the home page. The different one has its own link that we can click on. Step 4. Let's invent async components. You might have noticed that this part of the blog index page and blog post page components look exactly the same. The part with the header with the link to the page and the article underneath of it. It would be nice if we could somehow make this a reusable component. However, even if you extracted its rendering logic into a separate post component, you would still have to somehow plumb down the content for each individual post put inside of the article here. Currently, the logic for loading content for posts is duplicated between here and here. So we load it outside of the component hierarchy because the read file API is asynchronous, so we can't use it directly in the component tree. Let's ignore that file system APIs have synchronous versions. This could have been read from a database or a call to some async third-party library. Or can we load it directly in the component? If you are used to client-side React, you might be used to the idea that you can't call an API like fs.readFile from a component. Even with traditional React SSR, your existing intuition might tell you that each of your components needs to also be able to run in the browser, and so a server-only API like fs.readFile would not work. But what if you tried to explain this to someone from 2003? They would find this limitation rather odd. You can't fs.readFile? Really? Recall that we're approaching everything from the first principles. For now, we're only targeting the server environment, so we don't need to limit our components to code that runs in the browser. It's also perfectly fine for a component to be asynchronous, since the server can just wait with emitting HTML for it until its data has loaded and it's ready to display. Let's remove the content prop and instead make post an async function that loads file content via an await read file call. We have the async function post that takes in a slug. We define the content and then we try to read the file to put it into the content. Otherwise, we're going to throw not found with the error. It's a special error we'll use later to set the 404 code. And then we're just going to return the same post that we have been. Similarly, let's make blog index page an async function that takes care of enumerating posts using await read dir. And so we define the files by reading the dir, and then we make the post slugs, and then we map through them and use our new post component for each one. Finally, the top-level server handler can delegate all the rendering to the router. So we just create the server and we check what the URL is and send the HTML that the router tells us we should for that URL. Otherwise, it's a server error. But wait, we need to actually make async await work inside of the components first. How do we do this? Let's find the place in our render.jsx to HTML implementation where we call the component function. Since component functions can now be asynchronous, let's add an await in there. This means that the render.jsx HTML function itself would now have to be an async function, and calls to it will need to be awaited. With this change, any component in the tree can be async, and the resulting HTML waits for them to resolve. Notice how in the new code there is no special logic to prepare all the file contents for blog index page in a loop. Our blog index page still renders an array of post components, but now each post knows how to read its own file. Note that this implementation is not ideal because each await is blocking. For example, we can't even start sending the HTML until all of it has been generated. Ideally, we would want to stream the server payload as it's being generated. This is more complex, and we won't do it in this part of the walkthrough. For now, we're just going to focus on the data flow. However, it's important to note that we can add streaming later without any changes to the components themselves. Each component only uses await to wait for its own data, which is unavoidable, but parent components don't need to await their children, even when children are async. This is why React can stream parent components' output before their children finish rendering. So we're actually going to start a new virtual machine here because I'm tired of switching ports, but everything is going to be the same here. We have the new create server that relies on the router to send the right page for that URL. And so now everything works great over here, and we have async components loading their own data. Step 5. Let's preserve state on navigation. So far, our server can only render a route to an HTML string. This is great for the first load. The browser is optimized to show HTML as quickly as possible, but it's not ideal for navigations. We'd like to be able to update just the parts that changed in place, preserving the client-side state both inside and around them. For example, an input, a video, a pop-up, etc. This will also let mutations, for example, adding a comment to a blog post, feel fluid. To illustrate the problem, let's add an input to the nav inside the blog layout component JSX. We save this, go back to the home page, and we have a layout. And whenever we type in here and we click on something else, it resets the input. Notice how the state of the input gets blown away every time you navigate around the blog? This might be okay for a simple blog, but if you want to be able to build more interactive apps, at some point this behavior becomes a deal breaker. You want to let the user navigate around the app without constantly losing the local state. We're going to fix this in 3 steps. First, we're going to add some client-side JavaScript logic to intercept navigation so we can refetch content manually without reloading the page. Second, we're going to teach our server to serve JSX over the wire instead of HTML for subsequent navigations. Third, we're going to teach the client how to apply JSX updates without destroying the DOM. Hint, we're going to use React for that part. Step 5.1, let's intercept navigations. We're going to need some client-side logic, so we'll add a script tag for a new file called client.js. In this file, we'll override the default behavior for navigations within the site so that they call our own function called navigate. So we just add this event listener to the window where we're checking to see if you're clicking on an anchor tag. If it's not an anchor tag, we return. If you're holding Control or Shift to open it in a new tab or a new window, we return. Or if it's an external URL, we return. So we don't do anything on any of those. But if it's an internal link to one of the other pages on our site, we prevent the default behavior of the browser, and then we use the history API to push that new URL into the address bar. And then finally, we call our custom navigation function that we're about to make in just a moment. And then we check for pop state. Just in case anybody hits the back or the forwards buttons in the browsers, we still want our router to handle that. In the navigate function, we're going to fetch the HTML response for the next route and update the DOM to that. So we start off by defining the path name, and then we try to navigate to it. So the path name is going to be whatever is in the address bar, which we have updated with the history API to be the link that has been clicked on. So then we try to fetch whatever is in that path name, and we take the text that we get from that fetch. And we then replace the body tag with what we find inside of that fetch. We only want to replace what's inside of the body tag. So this code isn't quite production ready. For example, it doesn't change the document.title or announce the route changes for accessibility, but it shows that we can successfully override the browser navigation behavior. Currently, we're fetching the HTML for the next route, so the input state still gets lost. In the next step, we're going to teach our server to serve JSX instead of HTML for navigations. So we just need to make a few changes over here to help our server know how to do this. In our create server function, we now have it trying to send this script using this function over here. And so the way that that's going to work is that we just need to send the file over, but we are going to be editing this HTML, so it can't be constant anymore. And then we just add the script tag to the top of the HTML here. We save this, and we set some state up here. It still gets lost. But if you look over here in the network tab, you can see we're loading the client.js, and when we click on a link, we fetch the text for the link, and we do a client-side route instead. So how do we preserve this state with this client-side router? Step 5.2. Let's send JSX over the wire. Remember our earlier peek at the object tree that JSX produces with the $$ type of symbol.for React element? We're going to add a new mode to our server. When the request ends with $JSX, we'll send a tree like this instead of HTML. This will make it easy for the client to determine what parts have changed and only update the DOM where necessary. This will solve our immediate problem of the input state getting lost in every navigation, but that's not the only reason we're doing this. In the next part, not now, you will see how this also lets us pass new information, not just HTML, from the server to the client. To start off, let's change our server code to call a new sendJSX function when there is a JSX parameter. And so we'll just update this right here, and it just checks for it, and it deletes it, and then it sends it to the router. Then, in the sendJSX function, we'll use JSON.stringify on the JSX to turn the object tree above into a JSON string that we can pass down the network. So let's just add that right here. We'll keep referring to this as sending JSX, but we're not sending the JSX syntax itself over the wire. We're only taking the object tree produced by JSX and turning it into a JSON formatted string. However, the exact transport format will be changing over time. For example, the real RSC implementation uses a different format that we will explore later in the series. Let's change the client code to see what passes through the network. So we'll take this navigate function and put it in client.js right here. So we're just checking to see if the JSX parameter is there. And when we click on a link, it gives us this, which is not very useful. All we have is a props with the URL for that link. So that's not very useful. We were hoping to get a JSX tree, like with the HTML tags and everything. What went wrong? Initially, our JSX looks like this, where we're calling the router functional component with the URL prop. It's too early to turn this JSX into JSON for the client because we don't know what JSX the router wants to render, and router only exists on the server. We need to call the router component to find out what JSX we need to send to the client. If we call the router function with that URL as props, we get this page of JSX. Again, it's too early to turn this JSX into JSON for the client because we don't know what blog layout wants to render, and it only exists on the server. We have to call blog layout 2 and find out what JSX it wants to pass to the client, and so on. An experienced React user might object. Can't we send their code to the client so that it can execute them there? Hold that thought until the next part of the series. But even that would only work for blog layout because blog index page calls fs.readdir. At the end of this process, we end up with a JSX tree that does not reference any server-only code. For example, this is all just normal HTML right here. Now that is the kind of tree that we can pass a JSON stringify and send to the client. Let's write a function called renderJSX to client.jsx. It will take a piece of JSX as an argument, and it will attempt to resolve its server-only parts by calling the corresponding components until we're only left with JSX that the client can understand. Structurally, this function is similar to renderJSX to HTML, but instead of HTML, it traverses and returns objects. So if it's a string, a number, a boolean, or the JSX is null, then we don't need to do anything special. We just return it. If it's an array, then we use our renderJSX to client.jsx on all of the children. And then otherwise, we check to see if it's a component like div, which is a JSX.type string, in which case we just need to spread it out and return it with a props where we renderJSX to client.jsx. Otherwise, if it's a functional component, then we do our normal thing for that. Lastly, it could just be an arbitrary object. We just want to go over that and see if there's any JSX inside of it. So we look through each of the entries. So next we need to edit sendJSX to turn JSX like router into client.jsx first before stringifying it. So let's copy these over. And we edit our send.jsx function. And if we save this and go over, now if we refresh and we click on the link, we're going to get the type of JSX tree that we want, where it has the HTML, the head tag, everything that we want inside of it, the title, etc. Now clicking on a link shows an alert with a tree that looks similar to HTML, which means we're ready to try diffing it. Note, for now our goal is to get something working, but there's a lot left to be desired in the implementation. The format itself is very verbose and repetitive, so the real RSC uses a more compact format. As with HTML generation earlier, it's bad that the entire response is being awaited at once. Ideally, we would want to be able to stream the JSX in chunks as they become available and then piece them together on the client. It's also unfortunate that we're resending parts of a shared layout like HTML and nav when we know for a fact that they have not changed. While it's important to have the ability to refresh the entire screen in place, navigations within a single layout should not ideally refetch that layout by default. A production-ready RSC implementation doesn't suffer from these flaws, but we will embrace them for now to keep the code easier to digest. Step 5.3. Let's apply JSX updates on the client. Strictly saying, we don't have to use React to diff JSX. So far, our JSX nodes only contain built-in browser components like nav and footer. You could start with a library that doesn't have a concept of client-side components at all and use it to diff and apply the JSX updates. However, we'll want to allow rich interactivity later on, so we will be using React from the start. Our app is server rendered to HTML. In order to ask React to take over managing a DOM node that it did not create, such as a DOM node created by the browser from HTML, you need to provide React with the initial JSX corresponding to that DOM node. Imagine a contractor asking you to see the house plan before doing renovations. They prefer to know the original plan to make future changes safely. Similarly, React walks over the DOM to see which parts of a JSX every DOM node corresponds to. This lets React attach event handlers to the DOM nodes, making them interactive, or update them later. They're now hydrated, like plants coming alive with water. Traditionally, to hydrate server-rendered markup, you would call hydrate root with the DOM node you want to manage with React and the initial JSX it was created from on the server. It might look like this, where you call hydrate root on the document with the app. The problem is we don't have a root component like app on the client at all. From the client's perspective, currently our entire app is just one big chunk of JSX with exactly 0 React components in it. However, all React really needs is the JSX tree that corresponds to the initial HTML. A client JSX tree, like HTML with all the contents within it, close the tag, that we just have taught the server to produce would work. So we import hydrate root, and then we get the initial client JSX. So how are we going to do that? This would be extremely fast because right now there are no components in the client JSX tree at all. React would walk the DOM tree and JSX tree in a near instant and build its internal data structure that's necessary to update that tree later on. Then, whenever the user navigates, we'd fetch the JSX for the next page and update the DOM with root.render. So, fetch client JSX, root.render the client JSX. This will achieve what we wanted. It will update the DOM in the same way React normally does without destroying the state. So let's figure out how to implement these two functions. Step 5.3.1. Let's fetch JSX from the server. We'll start with fetch client JSX because it's easier to implement. First, let's recall how our JSX server endpoint works, where it renders the JSX to client JSX by stringifying it. On the client, we're going to call this endpoint and then feed the response to json.parse to turn it back into JSX. So we need to change our send-to-HTML function here to now bring in React and React DOM in an import map. And then we have our client.js down here as well. And so let's save this. And I forgot to bring in hydrate root and to define this function, even though we're not going to use it yet, just so it doesn't throw that error, so that you can see that whenever we click on a link, we're going to get the error that he's trying to get us to get, which says objects are not valid as a React child. So if we console log the client JSX and let's refresh here and see what we get, we can see that we are getting the HTML tag. Where did the double dollar sign type of go? It's gone. Without double dollar sign type of symbol for React.element, React on the client will refuse to recognize it as a valid JSX node. This is an intentional security mechanism. By default, React refuses to treat arbitrary JSON objects fetched from the network as JSX tags. The trick is that a symbol value like symbol.for React.element doesn't survive JSON serialization and gets stripped out by JSON.stringify. That protects your app from rendering JSX that wasn't directly created by your app's code. However, we did actually create these JSX nodes on the server, and we do want to render them on the client. So we need to adjust our logic to carry over the double dollar sign type of property despite it not being JSON serializable. Luckily, this is not too difficult to fix. JSON.stringify accepts a replacer function, which lets us customize how the JSON is generated. On the server, we're going to substitute symbol.for React.element with a special string like $RE. So we have the client JSX string, which we're now passing the replacer function into. And the replacer function, what we do is we check for the symbol for React.element, and then we're going to return $RE. But we're going to check to see if it's a string that just starts with the dollar sign, and we're actually going to add another dollar sign to that. On the client, we'll pass a reviver function to json.parse to replace $RE back with symbol.for React.element. So we have json.parse here with the reviver function in which we check for $RE and return symbol for React element, or we check to see if it's that string that we added the dollar sign to, and we want to just take that dollar sign off to make it exactly what you want. So I just need to change out the client JSX right here, the way we parse it. And then we need to add this new function in and save that. And then we'll go over to the server and we need to send the JSX this way with this new function. So we go down to the send JSX, which is right here, add our new function, and then we need to change the way json.stringify works with that. So now you can navigate between the pages again, but the updates are fetched as JSX and applied on the client. If you type into the input and click on a link, you'll notice that the input state is preserved on all the navigations except for the very first one. This is because we haven't told React what the initial JSX for the page is, so it can't attach to the server HTML properly. So if we go over here and we refresh, you'll see that the first time we type in, it's not going to actually save it the right way, but the second time that we type, it is still there. Step 5.3.2. Let's inline the initial JSX into the HTML. We still have this bit of code with the get initial client JSX and it's returning null. We need to hydrate the root with the initial client JSX, but where do we get that JSX on the client? Our page is server rendered to HTML. However, for further navigations, we need to tell React what the initial JSX for the page was. In some cases, it might be possible to partially reconstruct from the HTML, but not always, especially when we start adding interactive features in the next part of a series. We also don't want to fetch it, since it would create an unnecessary waterfall. In traditional SSR with React, you also encounter a similar problem, but for data. You need to have the data for the page so that components can hydrate and return their initial JSX. In our case, there are no components on the page so far, at least none that run in the browser, so nothing needs to run, but there is also no code on the client that knows how to generate that initial JSX. To solve this, we're going to assume that the string with the initial JSX is available as a global variable on the client. So in that case, we're just looking for a variable on the window with double underscore initial underscore client underscore JSX underscore string double underscore. And with that, we are going to use our revive JSX function. On the server, we will modify the send_HTML function to also render our app to client JSX and inline it at the end of the HTML. So we serialize the JSX payload after the HTML to avoid the blocking paint. So first we render JSX to client JSX, and then we create this string that we add on to the HTML with the new variable that we are placing on the window, and we are stringifying that client JSX. So we are escaping it as well. Finally, we need a few small adjustments to how we generate HTML for text nodes so that React can hydrate them. So let's make our changes real quick. All right, first off, we need to change up this get client JSX function right here. If we save that, and then on the server is where the rest of our changes are going to be. We need to add this variable to the window right here in the send to HTML function. And then we need to change up our render JSX to HTML function here. We're just going to go ahead and do this all at once because he changes quite a bit here. We're probably going to do a lot of copying and pasting from this point on, but this is all about the way it interprets strings. And so we just have to go through and look to see if each node is a text node, if it's an array. So now if we save this, we should be able to keep the text in the input. Look at that. That's the goal we originally set out to accomplish. Of course, preserving the state of this particular input isn't the point. The important part is that our app can now refresh and navigate in place on any page and not worry about destroying any state. Note, although a real RSC implementation does encode the JSX into the HTML payload, there are a few important differences. A production-ready RSC setup sends JSX chunks as they're being produced, instead of a single large blob at the end. When React loads, hydration can start immediately. React starts traversing the tree using JSX chunks that are available, instead of waiting for all of them to arrive. RSC also lets you mark some components as client components, which means that they still get SSR'd into HTML, but their code is included in the bundle. For client components, only JSON of their props gets serialized. In the future, React may add extra mechanisms to deduplicate content between HTML and the embedded payload. Step 6. Let's clean things up. Now that our code actually works, we're going to move the architecture a tiny bit closer to the real RSC. We're still not going to implement complex mechanisms like streaming yet, but we'll fix a few flaws and prepare for the next wave of features. Step 6.1. Let's avoid duplicating work. Have another look at how we're producing the initial HTML. First, we render the JSX to HTML, and then we also render the JSX to client JSX. Suppose JSX here is just the router with the URL of the root route. First, we call render JSX to HTML, which will call router and other components recursively as it creates an HTML string. But we also need to send the initial client JSX, so call render JSX to client JSX right after, which again calls the router and all other components. We're calling every component twice. Not only is this slow, it's also potentially incorrect. For example, if we were rendering a feed component, we could get different outputs from these functions. We need to rethink how the data flows. What if we generated the client JSX tree first? And so step 1 of send.html will be rendering the JSX to client JSX. By this point, all our components have executed. Next, we can just generate our HTML from that tree. So let's copy and paste that over. First, we can turn the component into an object, and then we turn it into a string, and that's how that works. Now our components are only called once per request, as they should be. Step 6.2, let's use React to render HTML. Initially, we needed a custom render JSX to HTML implementation so that we could control how it executes our components. For example, we needed to add support for async functions to it. But now that we pass a pre-computed client JSX tree to it, there's no point to maintaining a custom implementation. Let's delete it and use React's built-in render to string instead. So this works, it works fine. But instead, we are just going to bring in React, which means that we can delete our render JSX to HTML function. And we just need to install React DOM, because React DOM can do this much better than us. So now if we refresh, we have our page working much better because React is rendering it. So notice a parallel with the client code. Even though we've implemented new features like async components, we're still able to use existing React APIs like render to string or hydrate root. It's just the way that we use them is different. In a traditional server-rendered React app, you would call render to string and hydrate root with your root app component. But in our approach, we first evaluate the server JSX tree using render JSX to client JSX and pass its output to the React APIs. In a traditional server-rendered React app, components execute in the same way both on the server and on the client. But in our approach, components like router, blog index page, and footer are effectively server-only, at least for now. As far as render to string and hydrate root are concerned, it's pretty much as if router, blog index page, and footer have never existed in the first place. By then, they have already melted away from the tree, leaving behind only their HTML output. Step 6.3. Let's split the server in two. In the previous step, we've decoupled running components from generating HTML. First, render.jsx to client.jsx runs our components to produce client.jsx. Then, React's render to string turns that client.jsx into HTML. Since these steps are independent, they don't have to be done in the same process or even on the same machine. To demonstrate this, we're going to split server.js into two files. We'll have server_rsc.js. This server will run our components. It always outputs JSX, no HTML. If our components were accessing a database, it would make sense to run this server close to the data center so that the latency would be low. And then we'll have server_ssr.js. This server will generate HTML. It can live on the edge, generating HTML and serving static assets. We'll run them both in parallel in our package.json. So he brings in this concurrently library so he can run them both at the same time. In this example, they'll be on the same machine, but you could host them separately. The RSC server is the one that renders our components. It's only capable of serving their JSX output, so it only has the send.jsx function, nothing else. And then the other server is the SSR server. The SSR server is the server that our users will hit. It asks the RSC server for JSX and then either serves that JSX as a string for navigations between pages or turns it into HTML for the initial load. So it is responsible for bringing in the serialized JSX response from the RSC server and then creating that global variable that we use to rehydrate the page. We're going to keep the separation between RSC and the rest of the world, SSR and user machine, throughout this series. Its importance will become clearer in the next parts when we start adding features to both of these worlds and tying them together. Strictly speaking, it is technically possible to run RSC and SSR within the same process, but their module environments would have to be isolated from each other. This is an advanced topic, and it's out of the scope of this post. Okay, Code Sandbox is acting up on me again and I don't have the patience for it. So here in the client, we have this getInitialClient.jsx, which is asking for this global variable, which we define in the SSR. So this is just going to bring in this global variable, and then otherwise it just needs to parse the JSX that we are getting from the RSC server, which is responsible for all of the major logic. It has all of our components and stuff in here, but all it needs to do is send that JSX along to the other server to the client. Recap. And we're done for today. It might seem like we've written a lot of code, but we really haven't. Server RSC.js is 160 lines of code, out of which 80 are our components. Server_ssr.js is only 60 lines of code, and client.js is only 60 lines of code as well. Have a read through them. To help the data flow settle in our minds, let's draw a few diagrams. Here's what happens during the first page load. So, the initial load, the user requests the index page, which the SSR server gets from the RSC server, which sends back the React tree for that, which is processed into HTML and inline tree for the hydration of that page and sent to the user. So, in the real RSC implementation, each step is streaming, so you wouldn't actually need to wait for completion. And here's what happens when you navigate between pages. So the user asks for a certain page with the JSX search parameter right there on the end. It gets stripped off by the SSR server, which asks the RSC server for that. And then as it sends it back, we get the React tree for both of them. It never needs to be turned into HTML because React is on the client and it knows how to handle that. Finally, let's establish some terminology. We will say React server to mean only the RSC server environment. Components that exist only on the RSC server, in this example that's all of our components so far, are called server components. We will say React client, or just capitalize client, to mean any environment that consumes the React server output. As you've just seen, SSR is a React client, and so is the browser. We don't support components on the client yet in our implementation. We'll build that next, but it shouldn't be a huge spoiler to say that we're going to call those client components. So as you can see, he has these challenges at the bottom with like add a random background color, implement support for fragments, bring in React Markdown, add a comment section, and I have completed almost all of these. We have the random color, we go in here, we have our comment section. This Google link right here comes from the fact that we are using Markdown in our components. But the thing is, there's the fragment support. This is going to take a while to explain, and this video is already really long. So with this, I am actually going to bring this to a conclusion. Thank you very much for watching this, and if you have any interest in seeing how I solve these challenges, I'll release that video in the next couple days. Thank you very much for watching, and I'm excited about server components. You should be too. It's pretty cool, honestly. I think so.